Hi there, welcome back. What we've got here today is a power amplifier. It's a hybrid amp. It's got a tube preamp with MOSFETs on the output stage. Now this is a Counterpoint SA-100 tube MOSFET power amplifier. And this thing is quite popular. It has quite a following. And this one has got a very common fault, or had. And the common fault, unfortunately, is that it tends to blow the output MOSFETs. And the reason is actually probably bad design that gave it its good results. That might sound a bit enigmatic, but what they've done is they've actually paralleled MOSFETs. And they parallel them without any source resistor, any balancing resistor. And that means that if your MOSFETs are not exactly, or as damn exactly as can be, matched, they fight each other, and one of them will end up passing more current and blowing up, and then that tends to cascade through the whole output section. This is exactly what happened here, and this is the second iteration of a repair or an intervention. The first one I didn't record, and what it had done is, of the MOSFETs on the output, this has got 2 N-channel and 2 P-channel MOSFETs, a pair for each side. So we had 8 MOSFETs, 4 of them were blown, and fortunately I was able to get 4 that were fine. So what I did was I just put those 4 in, rebiased this thing, and I've had the amp working. It's a friend of mine's amp. It's been working for some time with these MOSFETs. Now, one of the suggestions made on the web, and there is some information on the web, including a schematic, which seems to be fairly accurate. One of the suggestions is that these MOSFETs get changed for these new MOSFETs produced by a company called Exicon. And they tend to work. They need to be biased differently. They need to be wired differently. But they're also lateral MOSFETs, and they tend to work quite well. So this friend of mine ordered a single set, because I still don't trust the matching procedure. Now the set he's ordered, I'll give you more details in a bit, are actually more powerful than the ones that are in here, so hopefully the one set will give enough power for this amp to work quite satisfactorily. This is the schematic that's available on the web, and this is by no means original, neither by myself nor by the manufacturers. This is reverse engineered by someone called Federico Poletti, and it's dated July 1999, so it's been around for quite a while. So let's see how this thing works. The part that we're interested in mostly is this section here, which is the output stage. And what it has is positive supply over there, negative supply over there. Positive supply and negative supply go through 5 amp fuses. It then feeds the drains of 2 N-channel MOSFETs over there and 2 P-channel MOSFETs over there. These MOSFETs are, for all intents and purposes, in parallel. The gate resistors are independent though. So you've got 2 gate resistors over here. 422 ohms is what he measured. Signal, positive going signal is fed here. Negative going signal is fed here. So these MOSFETs in parallel are then connected to the output, which is the speaker output, through a 6 amp fuse. He has drawn in these source resistors, but they don't exist in the amplifier. This is a suggested modification, and it actually makes sense as to why, and I'll explain it in a second. Now, these MOSFETs, these 2 and these 2, work in parallel. They share the current that's driven to the load on the positive half cycle and on the negative half cycle. They also have a static bias condition, which is fairly high at 100 milliamps per device, meaning that it's 200 milliamps going through that fuse, 200 milliamps going through that fuse. It's per device, but this is effectively the current path. So when you bias this, you put an ammeter across in place of that fuse, and you adjust the bias, which I'll show you in a second, till you get 200 milliamps. The problem is that 200 milliamps has to be shared between these two MOSFETs, and because this circuit is built without any of these resistors, for the two MOSFETs to carry exactly the same current, they must be very, very well matched. And it's very difficult to match MOSFETs even from the same batch. It's very unlikely that you'll get an equal, absolutely equal sharing of current, which is the problem with this design. If one MOSFET opens more than the other, it is going to hog the current, and therefore it's going to overheat. You think you've got a fair amount of balance going through, when in fact you might be burning out one or the other. So in the case that I have now, this one is gone and that one is gone, so I'm just using one pair. And because I'm using one pair, I can't drive this as high as the signal will want to go, because it'll require too much current for one MOSFET to handle. The new one, the Exicon, is double the power of these MOSFETs. So I should be able to drive this fairly high and have that MOSFET handle the current quite well. I'm still going to put in just the one each. Now, the problem we have is the bias. I can adjust the bias over here. This is a 10-turn pot, and I can adjust the bias condition by measuring the current at the same time as I adjust this pot and set the bias current to whatever I want. However, the way this sets the bias current is by creating a differential voltage between these 2 points, because at the top here you have plus 40, at the bottom here you have minus 40. So if this were a short, as is the case when the relays are shorted before the relays activate, I get 80 volts across 200k, which isn't much current. Now, if I open the relays, I then have this transistor driving that resistor with the voltage equal to the difference between these two. And that bias point is set with a spot. There's 100k, 23k, and 25k. So as I raise this, the voltage here rises, the drop across there stays practically constant, so the voltage here rises, more current is drawn, this voltage becomes higher. It's sort of a balancing act that this is doing. My concern is that these MOSFETs that I'm putting in here may switch on at a much lower voltage than the ones that the circuit is built with. So I need to be careful about what voltages are going to be at those gates when I put those new MOSFETs in and when I switch it on, because I could calculate it wrong and the inrush could blow them. So what I need to do is I need to ensure that I have a fairly good range of voltages here and start at very low voltages, let's say at plus 1.5, minus 1.5, and then adjust it accordingly to get the current that I want on there. The way to do that, to increase this particular voltage or decrease the voltage that I'm going to have across these two, is by reducing this resistor, because the voltage really is created by the current that this transistor is switching through to that resistor. So if you've got a current and you've got a lower resistor, you get less voltage over there, less voltage over there. So the difference is reduced. So what I'm going to do now is I'm going to place a couple of leads across this resistor and add resistors to those temporarily and try and get the right voltage swing that I need here to test the circuit when I first power it on. I can see what happens when I put it on, say, with, let's say, a 3K resistor in parallel with this one. That'll come down to about 2K. So I should get a much lower voltage. If that is too low, I can increase the resistor that I have in parallel with this till I get the range that I want. And that's what I'm going to attempt to do. While I'm doing this, I need to adjust the offset as well, because every time I change this resistor, the positive voltage and the negative voltage will not be the same values. They'll only be the same values when I adjust the bias, the offset, to get exactly the same amount positive as I have negative. In other words, to adjust where the ground is. That's what it does there. The other concern is that the MOSFETs that I have in there at the moment, the pinout, it's a TO3 package, similar to the Exicon ones that I've ordered. But what they have is the drain is the body. So the supply goes to the body of the MOSFET, and then you have the gate and the source. With the Exicon ones, it's different. The body is actually the source. So the easiest way to do that is to swap over the wiring that goes to the sockets where the transistors are fitted in. And I need to do that first. So that's the plan. So ideally, I should be able to run that new transistor also at 100 milliamps per device and get a pretty decent result. The MOSFETs I'm using were bought in the UK from a company called Profusion Audio Semiconductors. And the model I used a TO3 package, and it's the 20N20 and the 20P20. So these are N-channel and P-channel. So if we go to the service sheet, it's an N-channel. The drain to source voltage is 200 volts, drain current max of 16 amps, and the power dissipation, provided you have good heat sinking, is 250 watts. So it's double, I believe, what the other one was. And the pinout for this is body is 3, which is source as opposed to drain in the current ones. And then we have the gate over here, and there's the drain. So these two are reversed. And the way I'm going to go and sort that out is to actually just change the two connectors from the board to the contraption with the plugs that this plugs into. And that should do the trick. We hope. Those two diodes down here are the two diodes that are supplying the drains of the MOSFETs. So the current flows through in one way, out the other way through these two diodes. So to measure the current draw, all I need to do is remove the one and put an ammeter in series. I'm actually doing it on the other channel. I've already set it up. And I'm going to switch it on and show you the bias current and the bias adjustment, because we do have this pot over here which reads offset, and this one is to get 0 volts at the output. You can have a few millivolts, positive or negative, it shouldn't be a problem, but not too high. And then you've got this pot here, which someone in the past has converted into a 10-turn pot, thankfully. That thing sets your bias voltage and therefore the bias current at 0 signal. Now I have exactly the same thing on the other channel. This thing has the 2 preamp tubes just over here, and then it goes into the power section. It does have a speaker protection relay which takes quite a while to click in, and obviously we switch everything off when we swapping this out. So I'm going to show you how much current we've got there and how we can adjust it. These two, this is the ammeter. I've moved the fuse and I've connected the two leads to the opposite ends of the fuse, so the current flows through the ammeter. And over here I have a voltmeter, across the output and ground to measure the offset. So I've connected this to the power through the light bulb limiter, so we don't get massive inrushes if there's some sort of short, which I happen to know there isn't, but just in case, I have my ammeter ready. It's on a 1 amp range, DC amps across the fuse. I've got that across the output, and now I'm going to switch it on. The light on the front comes on red, which means the relay hasn't kicked in yet. It takes a while to warm up. As soon as the relay kicks in, that light turns to green. And there we go, it's just kicked in. And what you have here is practically 0 volts on the output, so very little DC offset. And we are reading just around 90 milliamps. It's now up to 100 milliamps. And that's pretty exact. Now it'll probably change somewhat as this warms up. But what I need to do is keep an eye on this, let it warm up for a bit, see what happens to the offset, see what happens to the current draw. Now, it's drawing 100 milliamps because I have 1 pair of transistors in there, and that's what I set it for. If I had 2 pairs, I would adjust it slightly because the second pair would start drawing current as well, and all the current on that leg is flowing through this ammeter, so it should be set to about 200 milliamps. In this case, 1 transistor pair, 100 milliamps. Now, what I need to do when I take this out and put in the other transistors, the other MOSFETs, is I need to be very, very careful to set the bias as low as possible. In other words, before I remove these transistors, I'm going to touch the bias and make sure this thing is down to about 20 milliamps, so that if the other transistors switch on earlier than these, I'm not going to short it out. Now I'll show you what voltage on the gates is actually producing this bias. So we've got, let me just adjust the bias a little bit and show you. If I go to the bias pot, there it's going up. It's going down. So I've got it on 100. My offset is practically 0. If I play around with the offset, there's minus 72 millivolts. It goes past to positive, and you just set it to as close to 0 as you can. And that's it. Now I'm going to let this warm up a bit. I'm then going to reduce that dramatically, because let me show you what I have on the gates. The gate voltage that's producing this bias current is minus 3.9 volts on the P channel and 4.15 on the N channel. So obviously when you adjust the bias, the most sensitive one is the one, or rather the slowest one is the one that takes longer to kick in, so these bias voltages can be slightly different. Now if I took the other transistors, the new ones, and put them in here, I don't know if 4.1 volts is going to short them, for example. It's going to open them out completely. So I need to put this far, far lower. And I'm going to do that now by reducing the bias current, and therefore that bias voltage. Let's see what we're getting here. This really won't go any lower. This thing is practically off, and the voltage I have here is 3.5. Now, what I don't know is if 3.5 is still not too high for the new transistors. It may well be. So I have to be very, very careful I have to put the dimmer, the dim bulb, on one light bulb only and try it out. Because if it doesn't satisfy the needs, then I have to change the bias setting, or rather the bias circuitry, to give me a smaller voltage. We've made some progress. What you're looking at here, minus 1.012 volts, is now the result of my tampering with the bias circuit to get the values down. If you recall, the MOSFETs in there were starting to switch on at about 3.94 volts. So the difference between the two, one was plus 4 volts, the other one was minus 4 volts, so we've got 8 volts difference. And so the bias voltage, the bias level, had to be somewhere above that, or slightly below that. In other words, this here would be about 8 volts. I've tampered with the bias circuit to the point where I can get the difference to 1 volt. Now, it doesn't matter that it's negative, it's just the other way around. But what it means now is that if the two MOSFETs are identical, if they're very well matched, half a volt will go to each. So you'll have plus 0.5 volts, minus 0.5 volts. That's the difference. It's not going to happen like that because they're not exactly matched, and one is a P-type and the other one is an N-type. But effectively, what I do now know is that I can adjust the bias, and I've connected this to the gates without the MOSFETs in there, okay? You don't want to play with that, with the MOSFETs in there when you're doing this adjustment. So I can go probably as high as, well, we'll see, won't we? This thing's a 10-turn pot, or is it a 20-turn pot? So I can adjust it. And what I'm going to do now is I'm going to leave it on the minimum. I'm going to put the MOSFETs in and very carefully bring it back up again by limiting the current as much as possible with the dimmer limiter. Seeing the result on the ammeter that I'm going to put across one of those fuses. And I want to get this to about 100 milliamps bias current with no signal. The reason I'm doing it slowly is because there can always be a few surprises. I have done some cleaning up. I replaced all the wiring that went to the MOSFET sockets because the wiring that was in here was getting a bit frayed. I've cleaned this up, checked all the solder connections, cleaned the contacts, tightened the sockets for the actual pins of the MOSFET, and put it back in. Might as well do a good job when you have this thing out. So I'm ready to try this with the MOSFETs now. So I'm going to put on the one lamp. The switch on the amp is off, and I'll put that on. As you can see at the moment, my mains is at 242 volts. When I switch that on, it's not going to do much because the relay, the protection relay, actually shorts the gates across each other and to ground for some time until the heaters warm up. So what I will do is I will switch it on and we'll see what happens on the first light bulb. Good. It flashed on while the caps are charging. It's now going dim. And as you can see, I've got 236 volts going into the amp. This is the effect of that light bulb on there. So while we wait for that to turn on, and always with your finger on the switch, because you never know what could happen when that gate voltage is... Oh, there it is. I was going to say that if this thing went crazy, you just switch that off right away. But what we have here, that's the ammeter across the one line's fuse. So that is the amount of current, 83 milliamps, that's flowing through the combination. That is the DC offset. So what I can do now, actually I'm going to give it one more light bulb so that I reduce the restriction of current just to get the voltage back to the mains level. It does have an effect, you see. We have 105 milliamps of bias current, there's no signal, and 0.4 volts of offset. So the first thing I'm going to do is try and null the offset. So I've got my screwdriver in the offset pot. It's the wrong way. And I'm keeping my eye on that current anyway. Oh, our offset's gone through 0. There's our offset pretty close to 0. Good enough for now. Good enough for now. And I've got 106 milliamps of bias current. I need to let this warm up a bit, but I'll show you what the effect of the bias pot now is. I turned it one way. There's still a little bit that I can drop. There we go. I can get it to 100. If I go the other way, I can probably get it up to 150 or so, but I won't try that. So I've got that at 100 milliamp bias, which is what I want to try it at. It's the same bias as I have on the original, and I'm going to try that for now. We obviously haven't seen a signal through this yet. This is simply no signal conditions, but I want to give it a bit of time and see that, just to make sure we don't have any magic smoke floating out of here. And I think we then do a signal test and see how this thing behaves. What I'm actually going to do is I'm not going to do both channels right now. You see, the conditions that I needed to change, or the components that I needed to change to achieve that bias voltage, were a little bit more complex than I at first thought. If you recall, I said I was going to change that resistor there, and I did. And the way I did that is I piggybacked a 1K resistor in parallel with that and soldered it on top. Very easy to remove if I have to. The other thing I had to do was I had to go further here. I couldn't get this low enough, and the way to get it lower was to drop that resistor. That resistor is now a 4.7K resistor in parallel with the 100K resistor. Now, that shouldn't be a problem because there's very little current flowing through that whole node. There's 100K there to the positive supply or negative supply, 100K to the positive supply. So there really isn't that much current flowing through there. I just reduced this so I can get this pot working in the range that gives me the bias voltages that I require, as opposed to plus 3.9, minus 3.9 or 4.1, whatever it was. It's now probably plus 0.5 minus 0.5, give or take a few hundred millivolts either way. So those were the two changes. R13, I put a 4.7K in parallel, and R60, I put a 1K in parallel. And that's what I had to do to get those ranges. Depending on the MOSFETs themselves, you may have to play with other values. The advantage of this is that you can actually test this without the MOSFETs in place. You remove the MOSFETs and you test the voltages there and there. Ideally, you test across the two connections, the two gates, because that'll give you the differential. It'll probably knock it off in relation to ground. In other words, when you measure this voltage in relation to ground, if you have a 1 volt across there, you might not get minus 0.5 plus 0.5 because this DC offset comes into play. But if you get that differential right, low enough, with a big enough span here so you can then adjust it, you can then just adjust the offset once you have the tested gate voltages done. So yeah, okay, that's what I'm doing. Let me show you the resistors. That's the first one, resistor 160. And there's the second one, resistor 113. I now have a 1 kilohertz sine wave at very low amplitude, well, fairly low, 50 millivolts RMS, going into both channels, the same signal. I have the speaker outputs connected to my distribution box over there. So left channel in there, right channel in there. I set both of them to 8 ohms dummy load, and then both of them are connected to the separate channels of the scope. So I'm now going to switch on the output from the signal generator and see what we get. Voila! We have the yellow trace is the left channel with the old MOSFETs. The blue trace is the right channel with the new MOSFETs. And as we can see, the gain on the right channel is slightly lower. The level is slightly lower. Now, obviously these are different MOSFETs, so I'm not going to worry too much about that. Let's center them. There they are. Actually, I'll increase the signal level a bit. Let me make it 100 millivolts RMS. Beautiful. Beautiful. And I'm just keeping an eye on the DC offset, and it is at practically zero, 5 millivolts. So that's great. Now, what I can do while I'm here is just do a quick check of the frequency response. Since I have the two channels together, I can actually compare them, which wouldn't be a bad thing. So let's try this at 100 millivolts RMS, 1 kilohertz. Let's see what kind of response we get if we do the left channel starting at 3.07 volts and the right channel is at 2.3 volts. Now this is in both cases obviously 1 kilohertz. Now I'm going to take it up to 10 kilohertz and see what happens. So we're at 10 kilohertz, we've got 2.83 on the left channel and we've got 2.23 on the right channel. So there's been quite a significant cut on the, well, more significant on the left channel than on the right channel, which means the new MOSFETs are reacting better to the frequency. So let's go up in, well, let's do 20 kilohertz. At 20 kilohertz, we've got 2.02 on the right, and we've got 2.34 on the left. So what we're seeing here is that the frequency response of the right channel, which is with the new MOSFETs, is definitely better. It's more steady, more flat than the old MOSFETs. There seems to be a roll-off on the older MOSFETs, actually quite early, even before 10 kilohertz. So what this should give us is what everybody is harping on about. It's probably going to give us a better high frequency response. It is going to give us a better high frequency response, and that probably means that we'll hear more treble, more highs, probably opening up the sound rather than creating a dampened one. But that, my friends, is what my buddy's going to tell me, because he's got ears that are absolutely incredible, unlike mine. And this basically is it. I'm going to leave the two like this, let him test it out. If he can't, it's going to be difficult because it will be a different sound. Even if you adjust the level of the preamp on the left slightly lower, you're still going to get a bit of a confusion. But the idea is then to do the left channel exactly the same as I've done this one. And so far, this seems to work quite well. I'm going to actually remove the left channel. I'm going to keep just the right channel, because what I want to do, let's trigger it on the right channel. What I want to do is actually take this up a bit further. We've got 2 volts, that's half a watt really, not much. But I'll take it down to 1 kilohertz again. And I want to see what happens when I raise the amplitude. So I've got 100 millivolts. There's 200. There's 300. There's 400. And I can tell you those light bulbs are starting to glow. But what we've got here is A very, very clean sine wave. It's looking beautiful. And I think we have a successful conversion. So guys, if that's what you want to do, I hope this video helps. I know that finding information on this particular amp and on this conversion has not been easy. There's actually very little information available. So I decided to do my own studying and then put as much of that together as I could. Remember to take it very, very slowly when you mess with the bias voltages before you put MOSFETs in. Be very careful. If you put those MOSFETs in and the bias is too high, too hot, you're going to get a surge of current and you could damage the MOSFETs even before you get them to work. So take it slow, be patient, and enjoy the result. Thanks for watching. Bye for now.